Bernoulli's number. Have you ever heard about Bernoulli's number? So if you haven't heard about Bernoulli's number, this video is for you. And in upcoming videos, I'll be discussing about the advanced conceptual use of Bernoulli's number, probably in Euler-Maclaurin formula. But for that, please do like, share, subscribe, and please support this video. And in today's lecture, we are going to derive some of the Bernoulli's number. So let's start the lecture. So let's define a function e raised to the power x. You must be very much familiar with this function, this exponential function, where e is the Euler's number, defined as limit as x tends towards infinity or n tends towards infinity, 1 plus 1 upon n raised to the power n, right? So this is the definition of Euler's number, and we are given fx is equal to this expression, okay? You must be very much familiar with the Taylor series of e raised to the power x about 0, or I can say Maclaurin series actually. 1 plus x divided by 1 factorial plus x square by 2 factorial and so on and so forth till infinity, right? How is it derived? You can derive it very easily. Fx is equal to e raised to the power x. So the Maclaurin series will be this function at 0, so e raised to the power 0 plus f dash of x will be e raised to the power x only, and at 0 divided by 1 factorial into x minus 0 raised to the power 1 plus e raised to the power 0 again divided 2 factorial times x minus 0 whole square and so on and so forth. So this is Maclaurin series, right, for e raised to the power x, right, or Taylor series about 0, okay? So this is the function fx, okay? And now let's change it a bit. So now let's see. Okay, first of all, let me write the definition, the Taylor definition, the Maclaurin definition of e raised to the power x. 1 plus x by 1 factorial plus x squared divided 2 factorial and so on and so forth till infinity. Now x divided by e raised to the power x minus 1 is given as the summation from n is equal to 0 to infinity bn x raised to the power n divided by n factorial, where bn is the Bernoulli's number. So this is the definition of Bernoulli's number over here. So now we have to find b0, b1, b2 and so on and so forth, okay? So how can we approach to this definition? Let's see. So clearly you can bring 1 to the left hand side, you will get e raised to the power x minus 1 is x by 1 factorial plus x square by 2 factorial and so on and so forth till infinity, correct? Okay. Now let's divide both sides by x, okay? So what we'll get? We'll get e raised to the power x minus 1 divided by x is 1 by 1 factorial plus x by 2 factorial plus x square by 3 factorial and so on and so forth till infinity, correct? Okay. So let's name it as some g of x, okay? Where I should write over here g of x is 1 by 1 factorial plus x by 2 factorial plus x square by 3 factorial and so on till infinity, correct? Okay. So we have e raised to the power x minus 1 divided by x is equal to some g of x, okay? Now let's take reciprocal on both sides. We will get x by e raised to the power x minus 1 is 1 upon g of x, correct? Okay. So now let me erase all this stuff and let's come back to this expression. So we had got x upon e raised to the power x minus 1 is 1 upon g of x, right? And now we want g of 1 upon g of x, that is this term x upon e raised to the power x minus 1 as this in form of this expression, right? So we can write it as a naught plus a1 x by 1 plus, or you can write it just like this, a1 x plus a2 x square and so on and so forth till infinity, correct? Okay. So now you have the expression e upon e raised to power, sorry, x upon e raised to power x minus 1 is equal to a naught plus a1 x plus a2 x square and so on till infinity. Correct? Now from here we'll be solving for a naught, a1, a2 and so on and so forth. Right? Okay. So we have x is e raised to power x minus 1 times the quantity a naught plus a1 x plus a2 x square plus a3 x cube and so on till infinity. And now let's write the Maclaurin series for a raised to power x minus 1. If you don't know what is Maclaurin series or Taylor series, let me write the expression. F of x is f at x naught plus f dash at x naught divided by 1 factorial times x minus x naught raised to power 1 plus f second derivative at x naught divided by 2 factorial times x minus x naught whole square and so on and so forth till infinity, right? And when you set x naught as 0, you get f at x is equal to function at 0 plus f dash at 0 divided by 1 factorial times x minus 0 is x raised to power 1 plus f double derivative at 0 divided by 2 factorial times x square and so on till infinity. This becomes the Maclaurin series when x naught is equal to 0. Correct? Okay. So now let me erase this and let's solve for these coefficients of x raised to power 0, x square and so on and so forth. Right? Okay. Okay, so we had got x is equal to e raised to the power x minus 1. What is e raised to power x minus 1? X by 1 factorial plus x square by 2 factorial and so on and so forth till infinity. Correct? Okay. So we have x by 1 factorial plus x square by 2 factorial and so on and so forth times correct. The original expression was x is equal to e raised to power x minus 1 times a naught a1x and so on till infinity. So I have just written the Maclaurin form of e raised to power x minus 1. Okay, right. So we have this expression. Now let's multiply all this stuff. So we will get a naught x by 1 factorial, a naught x square by 2 factorial plus a naught x raised to power 3 divided by 3 factorial plus of course till infinity, right? Now similarly let's write it for a1, a2 and so on and so forth. So for a1 it will be a1 x square by 1 factorial plus a1 x cube by 2 factorial plus a1 x raised to the power 4 divided by 3 factorial and so on and so forth till infinity. Correct? Okay. So now let's write for a2 over here. So what we'll get? a2 x square times this, we will get a2 x cube by 1 factorial plus a2 x raised to the power 4 divided by 2 factorial and so on and so forth, and rest all other terms like this. What will the first term in all the expressions? It will be of the form, suppose for a kth coefficient, this will be the first term over here, right? So when you substitute k as 2, you get this expression. When you substitute k as 1, you get this expression. When you substitute k as 0, you get this expression. Okay, right. So now let's solve for a naught. Okay, so yeah, I have already written over here. So now notice that on RHS we have bunch of algebraic expression which have infinite terms actually, and they all consist of powers of x, and on LHS we have just one x over here, which means that for this expression to be always true, the coefficients must be 0. What I mean is that for suppose for x, so we will have a naught x by 1 factorial, right? So the coefficient of x over here is equal to 1. So we will have a naught by 1 factorial is equal to 1. So we have a naught is equal to 1. Okay. So now we have got a naught is equal to 1. Okay. Right. Now let's bring to solve for a1 we have to bring the coefficient of x squares together. Okay. You can bring the x cube terms also together. There's no harm in that. Okay. So when you bring all the terms with x square together, then what we get? We get a naught x square by 2 factorial plus a1 x square by 1 factorial. Now you all can ask me that earlier I had said that you can bring x cube terms also together, but why I'm not doing that? Because I don't know the value of a2. If I bring x cube terms together, then I will get a naught x cube by 3 factorial plus a1 x cube by 2 factorial plus a2 x cube by 1 factorial. So I won't be able to find a1 over here because a2 and a1 both are variables over here, right? Now bring x square outside, you will get a naught by 2 plus a1 times x square. Now what is the coefficient of x square on LHS? It is equal to 0, which means that this term should be equal to 0. Then only this expression will be forever true, right? So we will get a1 is negative a naught by 2. So we get a1 is equal to negative 1 by 2. So a1 is negative 1 by 2. Correct? Okay. Now similarly, let's solve for a2. Now for a2 you have to bring x cube terms together. So a2 by 1 factorial plus what is the coefficient of x cube over here? A1 by 2 factorial plus plus what will get over here? A naught by 3 factorial, right? A naught by 3 factorial, correct? And now we will set it equal to 0, right? Because we want the coefficient of x cube to be 0. Because on LHS we don't have any x cube, right? So now let's solve for a2 over here. So a2, what is a1? A1 is equal to negative 1 by 2. So negative 1 by 2 will become negative 1 by 4 because 1 by 2 into 1 by 2. Okay. What is a naught? A naught is equal to 1. So plus 1 by 6, correct? So from here you get a2 is 1 by 4 minus 1 by 6 is equal to plus 1 by 12. Okay. So a2 is plus 1 by 12. Okay. Now let's solve for a3. So for a3, what you will do? I have written the general pattern. So a3 x into 3 plus 1, that is x raised to power 4 divided by 1 factorial. So what will it become? A4 divided by 1 factorial plus what is a3? It will be a3. Sorry. So a3 plus a2 by 2 factorial. A2 by 2 factorial plus what is a1? A1 by 3 factorial plus a naught by 4 factorial. A naught by 4 factorial is equal to 0. Correct? So from here you will get the expression a3. What is a2? A2 is equal to plus 1 by 12, right? So plus 1 by 12 will become 1 by 24 because we have 2 and there we have 1 by 12. So 1 by 12 into 1 by 2 is 1 by 24. Okay. Now what is a1? A1 is equal to negative 1 by 2, negative 1 by 2, and over here we have 3 factorial, that is 6. So minus 1 by 12, right? Plus what is a naught? A naught is equal to 1. So 1 by 4 factorial is 1 by 24 plus 1 by 24 and set it equal to 0, and when you solve you get a3 is equal to 0. Correct? Okay. So from here you must have noticed a pattern. So if you want to solve for a of k, you will need the expression ak divided by 1 factorial plus ak minus 1 divided by 2 factorial till a naught divided by k plus 1 factorial and set it equal to 0, and then solve for ak. Correct? Okay. So these are some of the terms. So a3 will be equal to 0, right? and this is how you will solve for all the terms over here. So let me erase this and let me tell you how to find Bernoulli's number from here. Okay, so we have solved for a0, a1, a2 and a3 and so on and so forth. We can solve using the relation ak divided by 1 factorial plus ak minus 1 divided by 2 factorial and so on and so forth till a0 divided by k plus 1 factorial and setting it equal to 0. Correct? Okay. So from here you can solve for further values. Okay. So now we have the expression x by e raised to power x minus 1. Let me write properly. X by e raised to power x minus 1 is a0. What is a0? a0 is equal to 1. So 1. What is a1? a1 is equal to negative 1 by 2. So we have negative x by 2 plus a2 plus x square by 12 plus a3 0 x cube by that is 0x cube. That is it. Okay, and so on and so forth till infinity, and you can solve for other values, other coefficients using this expression. Now we want as the summation from n is equal to 0 to infinity of the quantity bn x raised to power n divided by n factorial. Correct? Okay. So now you can write it as b0 divided by 0 factorial plus b1 x by 1 factorial, or you can write it as b1 by 1 factorial times x, or let it be like that, b1 x raised to power 1 divided by 1 factorial plus b2 into x square by 2 factorial and so on and so forth till infinity. Correct? Now to solve for the Bernoulli's coefficients over here, you have to just match the coefficients over here. So when you match the coefficient, you will get b0 by 0 factorial should be equal to 1. So you get b0 is 1, and for this you will have b1 by 1 factorial is equal to negative 1 by 2. So you get b1 is negative 1 by 2, right? For b2 by 2 factorial, for b2 you will write this expression is equal to, correct, because the coefficient of x square is 1 by 12 over here. So we have b1 is equal to 1 by 6, sorry, b2, and b3 by 3 factorial is equal to 0. So we have b3 is equal to 0, and likewise you can solve for all the binomial coefficients over here. Now suppose there is a term over here ak x raised to power k. Okay, so we'll have bk divided by k factorial is equal to ak. Correct? So we will have bk is k factorial times ak, and where ak is negative, the summation from, now this is a tricky part, ai divided by I going from 0 to k minus 1. So now we have to be careful over here. So it will be going from k plus 1 minus I factorial. This will be the function. So when I is equal to 0, you get a0 divided by k plus 1 factorial. It matches. When k is equal to, when I is equal to 1, you get a1 by k factorial. It is correct. When it is k minus 1, so when you substitute over here, you will get ak minus 1 divided by 2 factorial. You get this expression. So ak is equal to this expression. So you can write bk is equal to k factorial times negative the k factorial times the summation I goes from 0 to k minus 1 ai divided by k plus 1 minus I factorial. Correct? Okay. So this is the general formula for Bernoulli's number. Okay, over here, if you are using this thing. Okay. But why at the first place I am teaching this Bernoulli's number which seems to have no use in life or in mathematics? Then why am I teaching it? Well, it has lots of application, and in the next video I'll teach you about Euler-Maclaurin formula. Please check for the spelling, but okay. I'll teach you Euler-Maclaurin formula, which is very much helpful for approximations of the summation of the form f of k, where k goes from a to b. So in the next video I'll be teaching you this, and I had a comment from someone, so they asked me maybe in funny tone or maybe it was a general request for the video, that finding the summation of whole numbers using calculus. So yeah, this advanced calculus which I'm teaching you. So I'll first of all derive Euler-Maclaurin formula, and then we'll derive the summation of n, the first n whole numbers, using Maclaurin formula only. I mean Euler-Maclaurin formula, not Maclaurin formula. Okay. So I hope so that the basics of Bernoulli's number is clear, and of course this is very basic, and in next lecture you will get more detailed analysis of Bernoulli's number and some of its applications, right? For now you can practice calculating b5, b6 and b10. Okay, for homework you can do this. Okay, so till then, bye bye, take care and all the best.